All right, so we're going to start with example 10. So for 0 less than or equal to t less than or equal to 6, a particle is moving along the x-axis. The particle's position, x of t, is not explicitly given, so we don't know x of t. The velocity of the particle is given by v of t equals 2 sine e to the t over 4 plus 1. The acceleration of the particle is given by a of t equals 1/2 e to the t over 4 of cosine of t over 4. And x of 0 equals 2. Now, we're only looking at parts B, C, and D for this free response question. So we might not use all the information, but we'll use what we need to answer the question. So the first question says find the average velocity of the particle for the time period 0 less than or equal to t less than or equal to 6. So we're just trying to find the average velocity for the particle on that time period. So technically we're finding the average value of the velocity. So we're going to set up the average value of a function formula. So I'm going to do 1 over, and then this is my a and this is my b. So I'm going to do 6 minus 0, and then I'm going to do the integral from 0 to 6 of v of t dt, and this will end up being, I'll do 1 over 6. 1 over 6 times the integral from 0 to 6 of v of t, which is 2 sine of e to the t over 4 plus 1 dt. And if you type that into the calculator, you get 1.949. And then the next one says find the total distance. So total distance is going to be the integral of the absolute value of velocity traveled by the particle from time t equals 0 to t equals 6. So I'm going to set up my integral. It'll be from 0 to 6, and we're going to do the absolute value of the velocity function for this one. So we're going to still go from 0 to 6, and then we're going to do the absolute value of 2. Let's put the 2 in front. So 2 sine of e to the t over 4 plus 1. Close your absolute value, then put your dt. If you type that into the calculator, you get 12.573. So that's how you do those two parts of this free response question. And it was a calculator active free response question. Now we have one more question to answer. And this one says for 0 less than or equal to t less than or equal to 6, same setup, still have the same particle, still have the same formulas. For 0 less than or equal to t less than or equal to 6, the particle changes directions exactly once. Find the position of the particle at that time. So we're trying to find the position. So for the position, we're going to use the initial position, and then we're going to add the change to it. But we know that we're going to start at 0, but we have to figure out what's our other value of our integral going to be. And that's going to be when the particle changes directions. So we want to figure out what time the particle changes directions. Now, we have a function. We have this velocity function. And a particle changes directions when the velocity changes from negative to positive or positive to negative. And it only happens one time. So if I graph this function and I find out where it's equal 0 and where it changes directions, then I can figure out what that time is going to be. So if you take v of t and you graph it and you find where it equals 0 and where it changes directions there, you'll get it that it happens at 5.19552. And I wrote down the whole decimal just so I can be as accurate as possible. I'm not going to round to the end. So now I can go ahead and set up my integral. So I'm starting at my initial position is 2. So I'm starting at 2, and then I'm going to add the change from 0 to this time right here. So 5.19552 of v of t dt. And I'm going to go ahead and write that out. That'll be 2 sine of e to the t over 4 plus 1 dt. And if you type that into the calculator, you end up with 14.135. All right, so now we're going to talk about other functions besides velocity, acceleration, and position. So there are other rate of change functions that we're going to be looking at. And when you integrate a rate of change, you're going to get net change, okay, which we refer to as displacement if we're talking about the position of a particle. But it could be like water being pumped into a tank or people coming into a restaurant, something like that. So it's just going to be the net change. It's going to be, if you integrate from A to B, it's going to tell you how whatever, so if the rate of change is describing people, it'll be the people that changed from time A to time B. If it's talking about water, it'll be the water that changed from time A to time B. It's how much water was pumped into the tank or how many people entered the restaurant or, whatnot. And then I'm going to point out this formula down here. This right here will be our initial condition. We're going to have some initial conditions in some of these problems. So it might give us a starting point. And then this function right here is a rate of change function. And then this whole thing right here is going to be the net change. So if you know where you start and you know how much you change, you can figure out your final position or amount. So position, amount of water, amount of people, amount of money, whatever we're dealing with in the problem. That'll be your final amount there. All right, so let's start with a couple of examples. So example 11, a storm has washed away sand from a beach, causing the edge of the water to get closer to a nearby road. The rate at which the distance between the road and the edge of the water was decreasing during the storm is modeled by R of t equals e to the negative sign t feet per hour. So this is a rate of change function. The edge of the water was 200 feet from the road when the storm began. So this is an initial value, 200 feet. If the storm lasted for 4 hours, so that is our time, it's going to be 4 hours. How far is the water from the road after the storm? So we want that ending amount, ending position. So we're going to start with our starting position. So that's 200. And then we're going to add from 0 to 4 hours, because that's how long the storm lasted, of e to the negative sign t dt. And this you're just going to put into the calculator, and you will end up with 196.937 feet if you type that in. So that is going to be how far the water is from the road after the storm. So it started 200 feet, and now it's at 196.937. So you're losing a distance there, so the water's getting closer to the road. A store is having a 5-hour sale. The rate at which the shoppers enter the store, T, after the sale begins, is modeled by the function E of T. So E of T is a rate of change function, which is measured in shoppers per hour. When the sale starts, there are already 70 shoppers. So that is our beginning amount. We started with 70, right? But do not solve an equation involving an integral to find the time X. So we don't know one of the times, where the number of the shoppers in the store is 200. So we actually know our ending amount there. Assume no one leaves the store during this time. So this time we know how much we ended with. So we know what this is going to be equal to. But we're trying to figure out how much time passed. So we started with 70, and then we know what time started at 0, but we don't know the other ending part of the time of E of t dt. So this right here represents the change in shoppers. We just don't know what X is. This represented what we started with, and this is how many we had at the very end. So this is the equation that we would solve to figure out what time we had 200 people. Now, we can't actually solve this equation. We would need to know what this function was in order to be able to solve it. Now, example 12, we're given a table. Water is pumped into a tank at a rate modeled by R of t liters per hour, where R is a differentiable and increasing on 0 less than or equal to t less than or equal to 8. Selected values of R, t are shown in the table below. So it is differentiable. So it is continuous. At time t equals 0, there are 5,000 liters of water in the tank. So they do give us an initial condition here. What does the integral from 0 to 8 of R of t represent? So we're trying to figure out what that represents. Now, if we think about R of t as a rate of change, so if I go back to this slide right here, this actually represents the net change. Now, we got to put that in terms of what we're actually talking about here. So if I'm going back to this problem, what's changing? The amount of water in liters that are in this tank. So 0 to 8 of R of T dt represents the net change in water over the course of those 8 hours. Or we can say it's the water that's being pumped into the tank over those 8 hours. So it's the amount of water pumped into the tank over the 8-hour period. You could also say it's the net change in water in the tank over 8 hours. There's a lot of different ways you could word it, but I'm going to word it that way. And then it says to estimate the integral from 0 to 8 of RT dt using a left Riemann sum. Okay, now it doesn't tell us the subintervals. If it ever doesn't tell you the amount of subintervals, just use the ones provided in the table. So I'm going to have one interval from 0 to 1. Then I'm going to have another interval from 1 to 3. Then I'll have another one from 3 to 6. And then a final interval from 6 to 8. Okay, and I'm going to be using left Riemann sums, which means I'll be using the left endpoint for each of these intervals. Now, since they're in the table, all the widths are not going to be the same. So my first width from 0 to 1 is going to be a width of 1. And I'm going to be using the left Riemann sum, so I'm going to be using 3,000. And then I'm going to add the next one from 1 to 3, so that's a width of 2. And I'm going to be using 2,500. All right, the next interval is from 3 to 6. That's going to be a width of 3. And I'm going to be using the left endpoint there, so that'd be 2,100. And then the final interval from 6 to 8 has a width of 2, and I'm going to be using the left one there, which is 1,500. So those are all of my amounts there. And if you multiply and add all of those up all together, we get a total of 17,300 liters. Okay, so that is the amount of water pumped into that tank over that 8-hour period. Now, based on this estimate, how many liters of water are in the tank after 8 hours? So those are the amount that were pumped in. This is the amount that it changed by, but it doesn't mean that's the final amount in the tank, because we actually started with an amount of 5,000. So we're going to start with the 5,000. Then you would add that net change from 0 to 8 hours. And we already know what that is. We estimated it, so that's what we're using for this one. So 17,300. And we get a total amount, or a total estimation, of 22,300 liters. So that's how many liters we would expect based on that estimation to be in the tank after those 8 hours. Now, example 13, we're also talking about the same scenario. So still talking about water being pumped into a tank. But this time they give us the actual liter amount. So it still starts with 5,000 and we end with 22,000. So our estimate was a little bit off here based on the actual amounts that we see in the table. So it actually gives us the amount of water. So it actually gives us the liters. So it gives us WT. And then it asks us, what does the integral from 0 to 8 of W prime of T dt represent? So if W of T is the amount of water in the tank, then W prime of T would be the rate of change in water. Okay? Make sure that's not. That's going to be the rate of change of water. So when I integrate the rate of change, I get the amount of water over that 8-hour period. Because if I were to integrate W prime of T, I would get W of T. And W of T actually represents the amount of water. Now, this specifically is talking about the amount of water being pumped into that tank between 0 and 8. The W prime of T here is actually the same thing as R of T here, okay? Because R of T was the rate of change of water, and W prime of T is also the rate of change of water. So this is actually going to mean the same thing that we set that to mean in that first example. So to be amount of water being pumped into the tank over the 8-hour period. So the amount of water pumped into the tank over the 8-hour period. Now, the last thing we're going to find for this example is the integral from 0 to 8 of w prime of t dt. Now, you might recognize this as fundamental theorem of calculus part 1. So when you integrate a derivative and you have a definite integral that has endpoints, the integral from 0 to 8 of w prime of t dt, actually just when you integrate the derivative, you get back the original functions and you just evaluate it from 0 to 8. So technically what you're doing is you're doing w of 8 minus w of 0. And this right here is that fundamental theorem of calculus part 2. So I'm going to go ahead and plug these values in, and they're directly here in this table. So we're going to start with 22,000, and we'll subtract 5,000, which would give us a total change of 17,000 liters. Now that ended up being an exact amount because we actually knew the amount of liters. So we were able to find that without having to estimate. Where in the previous example, we had the rate of change function, so we had to estimate the net change, and it was 17,300. So we have like a little bit more of an accurate estimate for this one because we're not using Riemann sums. All right, last example is example 14. A balloon is being used to move sensors to different altitudes and is anchored to the ground by a cable on a winch. The graph made of 3 line segments represents V of t. So the graph is of V of t. The rate at which the cable is being let out or pulled in. So this is the rate at which that cable is being let out and pulled in, measured in meters per second, over a time interval of t, measured in seconds. At t equals 0, the balloon has an altitude of 10 meters. So we know we're starting at 10 meters at t equals 0. So that's our initial height there. Assuming the balloons move straight up and straight down, find the balloon's altitude at time t equals 540, 9 minutes after the experiment begins. Now this graph is a little bit small, so I'm going to kind of help you see the numbers on the graph. So the y-axis is going up by 10, so this is 10, 20, 30, 40, and 50. And the x-axis is increasing by 60. So 60, 120, 180, 240, 300, 360, 420, 480, and 540. So I'm going to go ahead and set up my integral. So I'm starting with 10, and then I'm going to add the integral of the rate of change function from 0 to 540 of V of t dt. Now this time I'm given a graph, so this right here, this right here is actually going to be the area underneath this curve. So it's going to be the area of this shape right here. Now, there's a lot of different ways you could do this. You could split it up into a rectangle or true triangles. You could also just treat it as a trapezoid. I think I'm going to treat it as a trapezoid. So I have the base down here. This base has a length of 540. The top here from 120 to 480 has a width of 360. So we have 540 along the bottom and 360 along the top, and then this height right here is going to be 50. So I'm going to go ahead and set that up. So it'll be 10 plus 1/2 times the base 1 plus base 2 times the height. And if I put all of that in, 1/2 times 540 plus 360, and then I add 10 to that, I end up with a grand total of 22,510 meters. That's my final altitude after those 540 minutes.